I want to close our discussion of the first law by talking about calorimetry, which is an experimental method for measuring changes in internal energy and enthalpy, in other words, for measuring delta U or delta H. There are two types of calorimetry that correspond roughly to measuring delta U or delta H. And in general, calorimetry involves measuring heat flows to or from a reaction using a surrounding or bath liquid whose temperature is measured inside a well-insulated vessel. We insulate the vessel so that we can imagine, ideally, that no heat is leaking beyond the bath liquid. So any temperature change in the bath liquid is associated with heat flows to or from the reaction mixture. Bomb calorimetry in particular uses a constant volume apparatus to measure the change in internal energy U. So remember from the first law that delta U is equal to Q plus W. But if the volume is constant, well then negative P delta V or negative P dV, the work or the infinitesimal work, must be zero, right? So in that case, Q, which we can measure by measuring a temperature change in the bath liquid, is simply equal to delta U. And so bomb calorimetry and that heat evolved or absorbed is a measure of the change in internal energy for the process. We run the process inside this calorimeter and then observe the temperature change. In theory, no heat leaks outside of the calorimeter, which is why we can treat the entire surroundings as just the bath liquid. Of course, in practice, there are some leakages of heat to the outside world, but if the vessel is insulated well enough, these heat flows might even be less than the precision of our measuring instruments. So in general then, we can say delta U of reaction is equal to negative Q for the bath liquid. In other words, the heat transferred, say, to the bath liquid must have come from the reaction mixture. That's why we use the negative sign. And that's equal to the negative, actually, of the mass of the bath liquid times its specific heat times the change in temperature for the bath liquid. This is easy enough to measure simply using a thermometer. Constant pressure calorimetry is actually much more common, and this is an experiment that you'll do in Chem 1211 or 1310. For constant pressure calorimetry, we run the reaction not in a rigid constant volume vessel, but in an open air vessel to measure delta H rather than delta U. The reaction takes place in a bath solution, which is usually water, and since expansion and contraction can occur, W may not be zero. But like we've seen for any constant pressure process, the heat evolved is equal to delta H. And since the heat is measured as a temperature change in the bath solution, just like for bomb calorimetry, we can write that the heat, say, absorbed by the bath solution is equal to the negative of the change in enthalpy for the reaction itself, or the negative of the reaction heat, the heat from the system's perspective. Using something like a coffee cup, which is not a very well-insulated vessel, we need to account for heat that's transferred to the calorimeter itself. And so instead of just accounting for the heat of the bath solution, I'm actually going to add another term in here, Q sub cal, heat transferred to the calorimeter walls. We can expand the heat for the bath solution the same way we did on the previous slide and write the mass of the bath solution times its specific heat times the temperature change. But for the heat transferred to or from the calorimeter, I'm going to use a slightly different form that uses the heat capacity, the C-cal of the calorimeter itself in joules per Kelvin times the temperature change in Kelvin, which would give us a heat in joules. So determining this C-cal is important in constant pressure or coffee cup calorimetry to get an accurate value for delta H of reaction. So how do we determine this C-cal value? Well, what we have to do is calibrate the calorimeter using, for example, a liquid such as water at known temperatures. So we're doing here a controlled experiment. We start with a mass of cool water at about room temperature, say 20 degrees C. You see that at the bottom left of the slide here. We add to that an equal volume and an equal mass of hot water at 80 degrees C, and we allow the mixture to come to equilibrium. In theory, assuming that no heat is lost to the outside world, the equilibrium temperature will be halfway between the hot water and cool water temperatures. That happens because we're using equal masses of the hot and cold water. That's not too difficult to show. All we need to show is that Q for the hot water is equal to the negative of Q for the cold water, and that's true because we're assuming no losses to the outside world. So the hot water is the system and the cold water the surroundings, for example. That means that M, the common mass, times C, the common heat capacity, since it's water in both cases, delta T for the hot water must be negative MC delta T for the cold water, which means ultimately, if we rearrange this, that the sum of the two, delta T hot water plus delta T cold water, must be equal to 0. And of course, the only way that this can be the case, such that the final mixture has a common equilibrium temperature, is if the final equilibrium temperature of the mixture is halfway between the initial hot and the initial cold, or 50 degrees Celsius. How can we introduce the heat transferred to the walls of the calorimeter into this mix? Well, we need to start with the same idea that the system's heat is equal to the negative of the surroundings heat, but we need to incorporate into the surroundings the calorimeter walls. So we can still write, for example, the system as Q hot and say that the heat transferred from the system must be equal to the negative of the heat transferred to the cold water plus the heat transferred to the calorimeter walls, all in parentheses, since these two will both be ultimately negative on the right-hand side of the equation. I'll leave it up to you to expand these and see how you could plug in actual temperature changes to calculate the C-cal. You'll actually do this in the calorimetry experiment.